Energy is a huge part of chemistry and basically every other discipline of science because it tells us what we have the capacity to do, what to change, okay? And it also helps us to figure out why something does or doesn't change. Some types of energy that we want to be able to recognize in science are shown up here. So we're going to go through kind of a little bit of each of them to talk about. So first up is kinetic energy. Kinetic energy is the energy of motion. Okay, anything that has mass and is moving at some speed or velocity has kinetic energy. Okay, so like this racquetball here. If I bounce it, that has kinetic energy. All right, if it had more mass or is going faster or both, it would have more kinetic energy. Okay, they're related to that. Okay, potential energy is a type of energy closely related to kinetic energy because they often interchange with each other. Okay, potential energy usually comes in two common forms in science. One is elastic potential energy, where you have some kind of springiness, all right, or elasticity in your material. So like for Slinky here. Okay, where it can kind of stretch and pull itself back up and back and down and up. Okay, that kind of ability to stretch or be compressed has to do with elastic potential energy. Essentially, the potential to move. Okay, the potential to change its position or its shape. Okay, to deform or to reform its original shape. The other kind of potential energy we see often in science is gravitational potential energy. So, anytime you hold something out like this and get ready to let it go, okay, it has gravitational potential energy pulling it down. It's the potential to drop, okay? Now, if I release it, it will drop. And there's actually, in this case, some elastic potential energy too, but you'll miss it if you blink. This racquetball, when it hits the ground, actually squishes a little bit, like that. You'd have to slow it down real far to be able to tell, and you can find all kinds of cool YouTube videos that will do that for you. But it squishes a little bit when it hits the ground, okay? That stores up some elastic potential energy that can convert back into kinetic energy. As the shape goes back, it bounces back upwards, okay? So, types of energy are not strictly kept from one another. You can change from one type of energy to another, just like kinetic and potential energy can change between each other. I have potential energy up here, and when I let it go, it changes to kinetic, and once it gets up back here and kind of reaches its peak, it's gained some more potential energy to drop again. Sound energy is a wave that has to travel through something, okay? So it has to have some matter to push around, all right? If you want to think of a wave with a spring, not a sprinky, a slinky, a spring or a slinky, okay? It's a compression wave usually that goes kind of like this. It goes in and out, okay? And it's got to have stuff to push, okay? Now, usually we think of sound energy as coming through the air because that's the most common to us. That's how we hear most things. But it's actually not the best way for sound to move. If your matter is closer together, like in a solid instead of a gas, then it's going to be able to push one on another, a lot easier. So sound actually moves easier through solids than through other materials, other phases of matter. So I've got this bike bell here, okay, that's got some gears on the inside, okay, and what this is supposed to do is as I twist this here, this little bar is supposed to hit the inside of the bell and make noise. Well, right now it's not doing much because I'm missing the cover of it. You may also notice, as a little bonus here, let me see if I can turn it the right way. Show it. There it is. There's a spring right there. There's elastic potential energy here that's converted into kinetic energy. Okay. Now, if I want that nice ringing sound to come out, so I can alert people that I'm coming on my bike, my very old-fashioned bike, in this case, I guess, I've got to have something on there for that thing to hit. Okay. Now, if I spin that wheel on the inside and I let things vibrate, it's almost too loud now. Okay, so sound is a wave that has to move through stuff. Okay, electric energy is essentially the energy of electricity. It's the energy of electrons moving, typically through a metal, usually a wire, something like copper or aluminum. Okay, so like this is an example here. I think this is a simple motor. Okay, and it's got some wires here. So typically we've got some insulation on the outside, some kind of rubbery plastic substance. Okay, but on the inside you've got some metal, right? And this is kind of braided together, kind of frayed out a little bit. Okay, so electrons pass pretty easily through metals, so that's kind of our top pick for something that conducts and moves electrons. Okay, and we'll talk a little bit later about kind of how we get electricity. But electricity, electric energy are essentially just electrons moving through something like a wire. Okay. Magnetic energy is the energy of magnetism. It's the energy associated with magnetic forces. Okay. These are a bunch of magnets here. I've got kind of on this little pole here. Okay, and they are resisting gravity, and essentially it looks like they're floating because they're pushing against each other. Okay, magnets can attract and repel, and they can do so at a distance. Typically, when we think of forces, we think of physically, pushing on something. You got to, actually put your force on the thing directly. But magnets can act at a distance. Okay, which is kind of their big thing. Okay, you can have attractions and repulsions at a distance. Okay, you can have attractions here. Oh, I grabbed one of them. I can grab another one here. Up, like that. Put those back there. Okay. I can also kind of get them to spring. If I try and push them closer together and they're going to repel each other, boom, I can actually flip that one off. I can attract or repel. There we go. Okay. So, magnetic energy is just the energy associated with magnets, pushing and pulling against each other. Okay. You can also have magnets move charges, which we'll, again, talk about later. Okay? Thermal energy is the energy of heat. Okay? Anything that is hotter or colder than its surroundings transfers heat from hot to cold. Okay? Never from cold to hot. Okay? Essentially, the energy associated with the change in temperature that's going on. Okay? But usually we're thinking of heat when we think of thermal energy. Okay? And how that heat moves from one thing to another. I've got a hot plate down here that you can't see, but it's essentially just a little disc, like a candle warmer would have. It's nothing, spectacular. You're not missing anything. And I've been warming up this beaker of water here. Okay, it's water. It started at about room temperature, which my temperature probe here is telling me is about 25 degrees Celsius. Okay, if I take my probe out. Okay, you can already see the numbers start to climb because my hand is relatively warm. Okay, now if I dip the probe into the beaker of water, we're climbing 37, 38, 39. Ooh, is it going to make it to 40? 40. Okay, and this is Celsius, so 40 might not seem like a high temperature, but in Celsius it's pretty high. Usually 20 to 22 degrees Celsius is room temperature. So if that tells you something. Okay, so use a hot plate to transfer heat to this thing to warm it up. A lot of hot plates, like this one here, work by essentially running electricity through something and having the heat come off it as waste energy. You can think of it like friction of electrons in the wire. So you have a bunch of electrons moving, and as they bump around and hit each other and hit the inside of the wire, you end up with this extra heat rubbing off and coming off. With the hot plate, we're essentially making that the point. A lot of times we don't want to lose that electrical energy through heat, but in this case, it's kind of the whole thing. So, again, types of energy can be tied together. Okay, electric and heat are often tied together in kind of our everyday appliances, even in, say, light bulbs. Okay, if you leave a light bulb on for too long, usually it gets hot. Okay, even if it's a pretty efficient wire, you're going to have some rubbing, you're going to have some electron friction, again, if you want to think of it like that, and you're going to have some waste heat. Heat is often sort of the waste product of the energy world. It kind of, comes off as, extra stuff that is just trying to, spread out. But during the winter, it can be real nice for us. We don't think of it as waste then. It's very useful. Okay? Now, speaking of lights, light is also a type of energy. Okay? Again, closely associated with electricity in our modern day. In this case, 2020 is the year I'm filming this in. But light is a wave that goes like this, okay, instead of like this. So it's a little bit tougher to do this one with the slinky, but if I can kind of like that. Whoop, I got too far. Hey, that's a little better. Where you've got kind of like peaks up and down and up and down and up and down that are opposite of each other. Okay? Now, light is also different than sound because it can travel through nothing. It can go through a vacuum where there is no matter. Okay? Which is why we can get sunlight all the way out from distant space to come to us. Okay? Even though there's barely any matter in between, the sun and us, those light waves can still make it to us. Okay? Whereas sound wouldn't. Sound, isn't really much of a thing in the vacuum of space, which kind of makes, Star Wars and Star Trek and all that stuff a little bit more boring if you wanted to be realistic about it. But, sometimes you gotta fake things a little bit to make it more exciting, in a movie. Anyway, so that's light energy. Chemical energy is the energy associated with chemical reactions. Okay? When we put together a chemical by its atoms, all right, it's held together by attractions. You can kind of think of it like magnets, a little bit. It's different, but kind of the same idea, where they can attract to each other and stick to each other. Now, when atoms stick to each other, we call those kind of sticking points bonds. All right, so they bond to each other. When a chemical reaction happens, we are rearranging those atoms and bonds to make a new chemical that is more stable. Okay? When we do that, all right, when we make something that is more stable, that means we don't need as much energy to hold that stuff together in those bonds. So that extra energy that we no longer need is released. Okay? A lot of times that energy is kind of released and either captured or used as electricity or heat, light, which is how you get all your exciting chemical reactions that blow up and have flames and things like that. Okay? So for instance, this butane lighter, okay, lets out a gas that I can combine with the oxygen in the air, and when I give it a little bit of a spark, it lights up into a flame. Okay? This flame is essentially just light and heat coming off of this chemical reaction between the liquid butane in here that turns into a gas when I release it, okay, and the oxygen in the air. Same goes for a candle here. When you think of what burns on a candle, you usually first think of the wick, but the wick also helps to draw up some of the wax, which is really the main fuel here. It's a lot of carbon and hydrogen that is very good for burning, kind of like the fuel inside here. Except this is even more unstable. It's this huge molecule that is just ready to be broken up. So we give it a little bit of energy and starts breaking and breaking and breaking into more stable pieces, and that extra energy is released as light and heat. All right. Now, nuclear energy is about the one thing I can't show you easily in the lab for cost reasons and for safety reasons, but I can give you something related. You just might have to trust me a little bit. Okay, so these marbles here have uranium in them. If I had a Geiger counter, a radiation counter essentially, I could stick it close to these and they'd start clicking, okay, because it would start picking up every time some kind of radiation came off of an alpha particle, a beta particle, a gamma ray, and it would just start bam, 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 making clicking noises every time some radiation came off of these. Now these are radioactive, but not enough to hurt me substantially unless I ate one. And I think I'd probably get more damage from eating the marble itself than, the radiation. Don't eat marbles, especially if they're radioactive. But anyway, so these have uranium in them, which makes them radioactive. It's a radioactive isotope of uranium. Okay, but aside from it being radioactive, uranium can be fluorescent, which means if I hit it with a strong enough beam of light like this black light here, okay, I can get them to fluoresce and glow and release light of a different color. So I hit them with this kind of purplish to invisible UV light, and I get out green light, okay? So now, is uranium the only thing that fluoresces? No, so you're going to have to kind of trust me that it is uranium in here that's causing the marbles to fluoresce. But that's about the best I've got right now. You can also look up videos of things called a spinthoroscope, which essentially are kind of like a little tiny kaleidoscope you look into to see the light emitted from nuclear changes, okay? Where, kind of the same idea, we have a screen that fluoresces every time radiation hits it instead of UV light, and you get all these beep, 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 little pings of light that you can see, okay? And people have been able to film that on YouTube. My camera doesn't, work well enough to film through my spinthoroscope, but you can find all kinds of stuff on YouTube. Okay, so those are our main types of energy, and we're going to use them to kind of walk through the world of chemistry and other sciences to figure out how the world works and why the world